Welcome back to our last unit of the year. We are getting into Unit 10, which is waves. So for Unit 10 and waves, we're going to start with Chapter 15, looking at waves and sound. So I wanted to start just by refreshing from Chapter 14, back when we did harmonic motion and oscillations, moving back and forth, because that's the start of a wave. A wave is a representation of the motion back and forth. So let's just review. A wooden toy hangs from a spring. When you pull it down and release it, it reaches the highest point of its motion after 1 second. What is the frequency of the oscillation? Okay, so here I go. I have a setup here. I got a point here. Oh no, wait, it's on a spring. Let's make it a spring then. Okay, so now it's on a spring. I pull it down and release it, and then it reaches its high point. So it goes from here all the way up to here. Now I know that a full wavelength would be a full up and then back down. So this is half of a wavelength, right? It's half of a full wave, half of a full up and back, half of a swing. So that means, sorry, the blue is 1/2 of a wavelength, just to clarify, right? The just up part. So it takes 1 second to do 1/2 of a full go. So that means it would take 2 seconds to go there and back, right? So it goes 1 second, one direction, 1 second, and then 2 seconds would be out and then back, 2 seconds. And I want the frequency. So 2 seconds would be the period. The frequency is 1 over the period, which is 1 over 2, which is 1/2, and so that would be D. All right, so just refreshing, coming back around to waves. So what exactly is a wave? A wave is a transfer of energy. Specifically, a wave occurs where you disturb the medium, and as the medium gets disturbed, we say the wave is propagating through the medium, so there's propagation happening through that medium, but the medium itself does not travel. So the medium is like the stuff. So as the wave goes through, the object itself might go up and down, but at the end, it ends back up in the same place. So the wave might be going this way, going through, object goes up and down, and then it ends back in the same place. It's not a current where the whole thing is moving. A wave, the energy passes through, but the stuff ends up staying in the same place. Okay, so waves transfer energy, but the medium itself does not travel. All right, so there's 2 types of waves that you'll likely remember from conceptual. So those 2 types of waves are transverse and longitudinal. A transverse wave, the motion of the wave is perpendicular to the direction of the wave speed. So in this case, the wave speed is going to the right, but the wave itself, the particles would go up and down. So here I'm going up, and so this is a transverse wave because I'm going up and down as the wave is going sideways. Now, a longitudinal wave can also be called a compression wave, because this is the one where they're going together and apart. So just to kind of refresh your memory, a transverse wave, an example of that would be light or anything on the electromagnetic spectrum. An example of a longitudinal wave would be sound. So when you are hearing my voice, it's because there are compressions and rarefactions. The areas that are tight are called compressions. The areas that are further apart are called rarefactions. And you can see that this is happening right here. So this right there is the compression. And that part right there where it's further apart is the rarefaction. Lovely. And in this case, the direction of the push and pull is in the same plane. It is parallel with the motion of the wave speed. So they're going in the same direction. So let's do a little stop and think. spectators at a sporting event do the wave, as shown on the photo on the preceding page. Is this a transverse or a longitudinal wave? Okay, so for the wave to happen, people are sitting in their seats. The wave is coming this direction. When it gets to them, they go up and then back down. So the wave was going sideways. The energy was going sideways. The person went up and down. So they moved perpendicular to the direction of the wave speed. And because of that, the sports stadium wave is a transverse wave. It is perpendicular, right? Perpendicular. It's going this way, but then the people are going up and down. All right, so let's talk about traveling waves. So as a wave moves through a string or through like a linear medium, we can figure out the overall force and the motion of it by taking a look at the tension on that string. So here we have tension going in both directions along the string. Remember, tension is equal and opposite on both ends of the string. So if the tension goes up here and down there, when we add them together, right, I take this, actually here, let me do this one in blue, and then I add the blue one in, I end up with a total net force straight up. So if I have a total force upwards, that's going to move the object up. Right, a push underneath will push it up. Then the wave has passed through. This wave is going over this way, sorry. The wave here has traveled along and now it's continuing to go this way. So the wave has passed through. Now, for this point right there, I've got down, I've got a little bit up, but it's at a different angle. So I add that together and it leaves me with my overall down net force. So the object will be pushed back down. Cool. Now, sound. Sound is a longitudinal wave. It is a compression and an expansion wave. So the compression is when the molecules are getting closer together. The rarefaction is when they're moving further apart. The compression itself is the disturbance, and it travels at the speed of sound. And then when those molecules are interacting with each other, we would say that it is a perfectly elastic collision. Because the molecules themselves are kind of like bouncing off each other, but remember electrons are all negative, so they never actually touch each other, so it would be perfectly elastic for the individual molecules of air. Okay. Now, if I were trying to figure out how fast a wave is going down a string, first I could figure out the string's linear density, and the linear density is the mass of the string divided by the length of the string. Then I could take that linear density and do the tension on the string divided by the linear density, take the square root of it, and that would give me my total velocity of the wave down the string. So that'd be the wave speed is the tension divided by the linear density of the string. Now for sound specifically, sound is often traveling through air. So we can use this very complex equation, square root of funny looking y times RT, T being temperature, divided by m, the molar mass. And it changes based on what the gas is made up of. So if it's a monatomic gas like helium, just a single atom, its multiplier is 1.67. Diatomic, like hydrogen or oxygen or nitrogen, would be 1.4. And then triatomic, carbon dioxide, water, would be a 1.3. Now, this is not actually going to be on the AP test, so we're going to kind of breeze through it, but it's interesting to think about. All right, now for our purposes, we are always going to assume, unless we are told otherwise, that the speed of sound in air is 343 meters per second. Now that would be at room temperature, which is 20 degrees Celsius. So, and that would also be at sea level. So at sea level, at room temperature, air is going to have a speed of sound through it of 343 meters per second. Now, obviously, if we change the temperature, if we make it colder, the air slows down a little bit because the air is a little bit thicker. If we made the air warmer, the air would get a little bit faster. You can also look at other objects. So you'll notice that the more rigid the material is, the faster the speed of sound is. So diamond is super hard, super rigid, and so it has a very, very fast speed of sound. Sound would move through diamond at 12,000 meters per second. That's really fast. And then through like metals like aluminum, 5,100, granite is rigid and stiff, so it would move at 6,000 meters per second. And then the less rigid stuff, like these liquids here, are more rigid than air, but less rigid than a solid. So that would be in the like 1,000 range. Okay. Other things to think about. The speed of light, just as a comparison point, is 3 times 10 to the 8th meters per second. That's 300 million meters per second, which is much, 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 much faster than the speed of sound. 300 million versus just 300, it's about a million times faster. So light does take time to get places, but it's a very short period of time. I mean, it's a long period of time if it's traveling through space, which is very large. Anyway, you guys get the idea. Depends how far it's going. But on the Earth scale, light moves real fast. Let's do a little life check. How far away is lightning going to be? During a thunderstorm, you see a flash from a lightning strike. 8 seconds later, you hear the crack of the thunder. How far away did the lightning strike? So this one is just a raw distance over time. Let's start with a needs and givens, old school. I need how far away, that is a distance. I am given 8 seconds, so a time is 8 seconds. And then I also know it's thunder, so that's a sound, and it's moving through air. And I'm going to assume the air is room temperature, 20 degrees. So I know that I have the speed of sound is 343 meters per second. Now I could use velocity equals distance over time. 343 meters per second equals an unknown distance times over 8 seconds. Multiply both sides by 8 seconds to cancel out, or make it 1. And then I end up with a distance of 343 times 8. 2,700 meters. Technically, it's 2,744. So that'd be about 2.7 kilometers, or converted into miles, there are 1.6 kilometers in a mile. So I could divide 2.744 divided by 1.6-ish. It's about 1.7 miles. Cool. So if you're seeing the lightning flash and then it takes a while and then you hear the thunder, it's far away. You don't need to worry about it. If you're seeing the lightning and hearing the thunder at the same time, it may have struck you. It's very, very close if they're coming at the same time, because light travels almost instantly and sound takes a lot longer. All right. So let's do a stop and think. Suppose you shake the end of a stretched string to produce a wave. Which of the following actions would increase the speed of the wave down the string? There may be more than one correct answer. If so, give all that are correct. Okay. So to increase the speed of the wave, move your hand up and down more quickly as you generate the wave. No, that would increase the frequency, but the wave speed would stay the same. The wave speed is based on the material, and so that always stays the same. And we could also just refresh our memories. We know that the wave speed on a string is based on the tension and the linear density. And the linear density is based on the mass divided by the length. Okay. Move your hand up and down a greater distance as you generate the wave. No, that would change the amplitude, right? How high it goes, but it wouldn't change the wave speed because I'm not changing anything about the string. I'm not changing the tension. Use a heavier string of the same length under the same tension. Okay, so same length. Oh, but this one I'm looking for the increase of the speed. So if I look at my equation again, it was velocity of the string, wave speed, is square root of tension over linear density. So V equals square root of tension over linear density, and then linear density was the mass over the length. Yep. Okay. So if the length gets heavy, nope, length is the same. The mass gets bigger. So that means that this is going to get bigger, which means this is going to get bigger. So the wave speed will get less, right? Because I'm doing the denominator gets big, so the velocity would get smaller. And I need an increase in the speed, so that's a no. That would change it, but okay. Use a lighter string of the same length under the same tension. Yes, because that's the opposite, right? I just figured out that increasing the mass would decrease the wave speed, so that is a good one. Stretch the string tighter to increase the tension. Okay, so now I'm increasing the tension. If I increase the tension, that will increase the wave speed. So that is also a valid one. Loosen the string, that would do the opposite. So that's a no. So it would be D and E. Nice. All right, so let's take a look at a wave traveling down a string. So in this case, it's going to be like a sharp wave, not a sinusoidal smooth wave. So we have a sharp wave traveling down a string, kind of triangular. And you can see that this is Y up here and X along here. So this is showing a position versus height graph. So like X versus Y, it's basically a picture of the wave. So if we take a look, then we can see that as it moves, I have a change of X, right? And then it moves again, and it just kind of at different time periods, I could represent it as here, and then over here, and then over here. So it's moving along the string at different points. And it moves using the normal kinematic functions. The change of distance is the velocity times the change of time. Okay. Now, what if instead of doing it that way, I want to take a look at kind of like how it moves and look at what's happening to the actual position. So if I say time 1 right here, the object is that high. So at time, now I'm going to turn this into a YX graph to a Y versus T graph. So as the time passes, how high is it? I'm just switching, looking from position to time on my x-axis. So at x equals 1, I'm there, and that's at t equals 1. So t equals 1, I'm going to be at that point. Then t equals 2, I'm up there. So at t equals 2, I would put myself in that position. T equals 3, I am back down low. So t equals 3, I would be low again. And then t equals 4, I am down on the ground right there. And so t equals 4, I'm going to be back down on the ground. So I just took those points and translated them onto a time scale. All right. So let's try it this way. The figure at right is a snapshot graph of a wave moving to the left. The wave is to the right of the origin, but it will reach the origin as it moves. Construct a history graph for the motion of the marked point at the origin. So I'm going to that point right there. Okay. Following the approach showing in figure 15.7. Which of the graphs below is the correct history graph? Okay, so thinking about this, parts that it'll hit first. So first, as it's moving this way, right, as it's shifting this way, the first part that will go through the origin is an up and then a down, right? So I'm going to start with an up and a down. And looks like this one here starts with an up and a down. And it's a small up and down. And then it'll go through here, and then it'll have a big down, and then a big back up. So then it'll have a big, a big down and a big back up. So that shows me this one, A. So as it moves through, it'll give that shape over time. All right, let's head back up and we'll get into the meat of this one. So the meat of this is looking at what a wave is. So this diagram is going to be really key. And I'm just going to kind of point out some vocabulary, which hopefully will be review. So to start, this is a position versus time graph. So the distance between two crests, point to point, is the wavelength. Okay? The wavelength is crest to crest, or you could also measure it trough to trough. Trough is the low point. That is also a wavelength. Or I could go from going up at the origin to going up for the next time on the origin. That is also one wavelength, right? As long as it's the same position in the wave, you're good to go. Crest is the top, trough is the bottom, and then the height, the total elevation that it reaches from the origin, from neutral. So it's from neutral to the top or neutral to the bottom. So from here up to here, right there, that is the amplitude. Or I could also represent it from neutral down to the trough as amplitude. Okay, so the amplitude is neutral up or neutral down. And then the wave speed is how fast it's moving off to the side. Okay, now if I graph it using time as my axis instead of position, remember last time I was using position as my axis. Now, instead of having point to point be the distance, the wavelength, now it's a time. So there, distance to distance, is the period, the amount of time it takes to go from one crest to the next crest, because the axis is time. And over here, oops, the axis was position. So position is meters, and that wavelength would be meters. All right. So the huge, big idea for this one, I'm going to make it whole screen. Here we go. For sinusoidal waves, waves that have the curly shape, the wave speed is equal to the wavelength times the frequency. This is the big equation. It's the only equation for waves, literally the only one that they give you on your AP cheat sheet. So wave speed is wavelength times frequency. Now, if I manipulate it just a little bit, I could say where that comes from. Well, it comes from velocity is distance over time. And in a wave, the distance is the wavelength and the time is the period. And remember, period is 1 over frequency. So 1 over t makes f. So velocity is equal to wavelength times frequency. Okay, both work. All right, let's do a little stop and think. 3 waves travel to the right with the same speed. Which wave has the highest frequency? All 3 graphs have the same horizontal scale. Okay, so they're all traveling with the same speed. I can see that the V arrows are the same. So since velocity is equal to wavelength over period, right, distance over time, as I get a smaller wavelength, say velocity is constant, so I'm going to make that a constant. As the wavelength gets smaller, the period also has to get smaller, right, in order to keep it equal. 5 over 5 is the same as 4 over 4 is the same as 2 over 2. So if the period gets smaller as the wavelength gets smaller, the frequency, which is 1 over the period, and as the period gets smaller, the frequency is going to get bigger. So I need a system where, in order to get a higher frequency, I need a smaller wavelength. And so the one with the smallest wavelength here is where that value is the littlest, and that is B. So we could also say that wavelength is inversely proportional to frequency. Right? I have an inverse proportionality there. as wavelength gets smaller, frequency gets bigger, or I could write it the other way. Frequency is inversely proportional to wavelength. Cool. All right. So let's go back and look at sound waves again. We already said that sound waves have compressions and rarefactions, and that the speed of sound goes horizontally as the air molecules compress and rarefy with elastic collisions. Now, we could also draw it like a transverse wave. This is kind of funky, but it's easier to draw the sine wave. Even though the sound itself is not traveling up and down, I could still represent it with a sine wave, showing high values would be compressions, high pressure, right? This is notice that the y-axis here is pressure. The middle value is atmospheric pressure, so that would be like neutral, just air pressure. So high values would be compressions, low values would be rarefactions, and they track perfectly compression, 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 rarefaction, rarefaction, rarefaction. Okay. Cool. All right. Let's do a little range of wavelengths of sound. So what are the wavelengths of sound waves at the limits of human hearing and at the mid-range frequency of 500 hertz? And the sound of human voices singing is about 500 hertz, as are notes in the middle of a keyboard. Okay, so we're going to assume that we have a wave speed of 343 meters per second at 20 degrees Celsius, and then it helps to know what is the range of human hearing. So here's humans, 20 to 20,000 hertz, and I need the wavelength. So I'm trying to solve for wavelength. The equation that I've got is V equals wavelength times frequency. So if I start with V equals wavelength times frequency and solve for wavelength, that gives me wavelength equals V over F. So I just need to take my speed of sound divided by my frequency in hertz. So at the low range is 20, wavelength equals 343 meters per second over 20 hertz, which is 1 over seconds. The 1 over seconds will cancel, leaving me with 343 over 20 is about 17 meters. So that's the lowest we can hear is a 17-meter wave. That is larger than this classroom, which isn't, it's pretty big, right? Pretty significant. All right. Then the low end is 20,000 hertz, so it's going to be the same thing, but with different values. Wavelength equals 343 meters per second over 20,000 1 over seconds. 343 over 20,000 is 0.017 meters, which is 1.7 centimeters. So the smallest wave we can hear is 1.7 centimeters, itty bitty. And then lastly, what about at 500 hertz, which is kind of like the sound of my voice-ish? For that one, wavelength equals 343 meters per second over 500. 343 divided by 500 gives me 69 centimeters. Cool. All right. So a refresher that we also have the electromagnetic spectrum. Electromagnetic spectrum has a whole bunch of different types of light on it. Visible light is what we're familiar with. That runs from 700 to 400 nanometers. A nanometer is like times 10 to the negative 9 meters. So these are very, very, very small transverse waves. Sound, remember, was a longitudinal wave. But then radio waves are also on there. AM radio, FM radio are bigger waves, like 300 meters down to 3 meters. Microwaves that heat up your food are very, very small. They're about 3 centimeters in size. And that's why the microwave spins around, because it's a 3 centimeter wave. So if it hit the same points every time, you'd get little hot patches and cold patches. So it spins the food around so that it heats up all the parts evenly. Then infrared is getting smaller, visible, ultraviolet, and then X-rays are extra itty bitty small. And that's why X-rays can go through your skin, because they're smaller than your skin itself. Okay, almost there. So comparing two different types of electromagnetic waves, infrared and ultraviolet, we can say that, so infrared and ultraviolet, wavelength and frequency, we'll just check the thing. Infrared and ultraviolet. Infrared has a smaller frequency. Okay, and infrared has a bigger wavelength. So longer wavelength, lower frequency. So that'd be C. And that's just based on reading the title or reading the chart and saying 10 to the 12th is less than 10 to the 16th, but 10 to the negative 4th is more than 10 to the negative 8th. Okay. Wave energy and intensity is not actually covered in the AP test, but I pulled this stop and think just because I think it's interesting. A plane wave is a linear wave, right, going in a straight line. A circular wave is going out in all circular directions. And then a spherical wave is going out in all directions three-dimensionally from there. All have the same intensity. Each of the waves travels the same distance. Afterward, which wave has the highest intensity? So I just like this question because it kind of lets you think about how things move and spread out. So which one's going to spread out more and thus reduce the amount of intensity? Remember, energy is neither created nor destroyed. Intensity is kind of like the energy of the wave. So the more it spreads itself out, the less intensity it'll have. In this case, the spherical wave will have to go in 3 dimensions. So it'll lose lots of, I mean, it'll have the same intensity, but it'll be reduced per unit of space, right? So it's per square centimeter or whatever. It's going to have much less. A circle goes out and it'll slowly get less and less and less as it goes further and further out, like on a pond, if you drop a pebble. And then the plane wave should stay the same intensity the entire time because it's going just on a straight line. So it should just keep going without friction, the same intensity the whole way. So the plane wave is going to have way more intensity because it doesn't have to share or spread that intensity out over any additional space. All right, another little reviewer. Amy and Zach are both listening to the source of sound wave that is moving to the right. Compare the frequencies that each hear. So this is the Doppler effect. If the wave is moving in this direction, then as it keeps making waves, the source of the wave is going to like catch up with the waves that it's making here. And so Zach will get all these waves really fast. Amy, it's moving away from her. So every time it makes a new wave, the next wave is almost to her. And so she's getting them further apart. So Amy will have a lower frequency. Zach will get a higher frequency. And that's why if you hear an ambulance coming towards you, it's high-pitched coming towards you, like, and then low-pitched as it goes past you. As it goes, that's not really the sound of an ambulance, but race car? Race car. I know that there's a lot of race cars driving past you all the time. So it goes high-pitched, low-pitched as it comes towards you and then away from you because the waves like stack up and then spread out. So the frequency, Zach's frequency would be greater than Amy's. C. All right, we're going to do one last practice problem, and we're just going to do the first couple parts of it. So earthquakes are dramatic slips of the Earth's crust. You may feel the waves generated by an earthquake even if you're some distance from the epicenter, the point where the slippage occurs. Earthquake waves are usually complicated, but some of the long period waves shake the ground with motion that's approximately simple harmonic motion. This graph down here shows the vertical position of the ground recorded at a distant monitoring station following an earthquake that hit Japan in 2003. This particular wave traveled with a speed of 3,500 meters per second, which kind of makes sense. It was going through the Earth. Oh, it's not the speed of sound, though. Never mind. But it's, in the thousands, which is reasonable. All right, was the wave transverse or longitudinal? Okay, so looking at the graph, it appears to have motion on the y-axis, which means it's going up and down. But I know that the wave was moving this way at 3,500 meters per second, and it's going up and down by like 40-ish meters per second, 50 maybe. So it is definitely transverse. The motion is perpendicular to the direction of the wave speed. And then what were the wave's frequency and wavelength? Okay. So for frequency, I can figure that out based on the graph, because here is in time. And so what I can do is I can say, well, here's the start. The next one right here, I'm just going to give it some space so I have some wiggle room, is 60 seconds out. And then I go 1, 2, 3, 4, 5, 6 waves in 60 seconds. So for frequency is 6 waves per 60 seconds, which would be 1/10 1 over seconds. And the unit for frequency is 1 over seconds, or hertz, which is 0.1 hertz. So now I have a frequency, and then the wavelength, I can use the speed and the frequency, because I don't actually have a wavelength value. There's no x value here. I'm only given the time and the amplitude. And the amplitude is not the same as the wavelength. It is a distance, but it's a vertical distance, and I want the horizontal distance. So for the wavelength, I could say velocity is wavelength times frequency. Velocity is 3,500 meters per second equals the wavelength times 0.1 hertz. I'll have to divide both sides by 0.1, 0.1. And that gives me 3,500 divided by 0.1, a wavelength of 35,000, oh my gosh, meters. So that's a wavelength of 35 kilometers. That is a very small, or a very large wavelength. So that's obviously outside of the range of human hearing, right? Humans, we said, could hear up to 17 meter waves, although that's a compression and expansion wave, and this one's a transverse wave. So anyway, all right, so that takes us to the end of chapter 15. We're going to do some practice questions, and then the meat of waves comes in chapter 16. And since the lights have gone off on me, I think it is time to finish. All right, enjoy, my friends.